We are here in Monteverde, Costa Rica, a tropical district in the Tiburon Mountains. The weather in this region consists of three main seasons: dry, windy, misty, and wet. The average rainfall per year is about 3 meters. The heavy rainfalls during the wet season lead to high erosion rates. It's important to consider these extreme conditions when constructing buildings, infrastructure, and specifically in our case, retaining walls. At the CIEE Study Center in Monteverde, a study abroad campus for students studying sustainability and the environment, the city recently installed a sidewalk next to the road, above a steep slope only about 3 meters away from the building site. Though the installation hasn't affected slope stability yet in the dry season, the erosion potential of the site is very high in the wet season. We have proposed the construction of a retaining wall to address erosion, structure, and aesthetics.
The site conditions pose one major design concern: soil stability. The soil composition consists mainly of rock and clay as well as organic soil, which experience oversaturation rather quickly and can in turn destabilize the slope. The maximum angle at which slopes are inherently stable is known as the angle of repose. An angle of repose can be influenced by factors such as water saturation, vegetation, and soil composition. This site's slope ranges from 55 degrees at its steepest to about 35 degrees. We need to address these steep angles to achieve a natural angle of repose for the soil. By constructing a wall of 1.75 meters at the steepest points, the slope of the backfill will decrease greatly, resembling a more natural angle of repose. When designing this wall, we kept several sustainable factors in mind within the local context of Monteverde. We considered geology, water flow, material availability, cost, educational value, environmental impacts, aesthetics, longevity, and structural integrity. From these parameters, we chose to implement 3 different methods: tires, super adobe, and carbon bottles. The method utilizing tires has several benefits. We obtained used tires from local gas stations and auto shops that were bound for landfills. The tires were virtually free, and they were diverted from the landfill to be used to create a functional retaining wall. The time required to build a tire wall is minimal compared to other methods. Though it requires a lot of physical labor, the quickness with which it can be constructed is essential for our time constraints. To actually construct the wall, we first established a line across the whole length of the wall that we wanted the tires to align to. Then we removed a tire's width of dirt into the hill. We laid the tires down between the trees and leveled them. We filled them with wheelbarrows full of dirt, packed them a little by hand, added some water, and used a sledgehammer to pound the dirt into the sides. After compacting the dirt more and more, it was always necessary to add more dirt. To finish the tire off, we tamped the earth down in the center to flatten it. By doing this to each individual tire, we developed a matrix of offset tires at each level to construct the wall.
In the second phase of this construction, we utilized an earth bag building technique called super adobe. We began by leveling the foundation where the retaining wall will eventually stand. To aid in drainage, we dug a trench 30 centimeters deep and 50 centimeters wide, filling with medium-sized stones we found in excavation. Each earth bag is comprised of a tube-like section of polypropylene bag and a composition of earthen material. This earthen material is 2.5 parts earthen clay, 2 parts fine sand, and 1/2 part cement. To mix the material, we used a manual mixing technique. Employing a canvas, we pulled the material over itself until the material was evenly mixed. Creating a hole in the center of the material, we added 1/2 part water, slowly with a shovel at first, and then continuing with the canvas technique until the moisture was consistent throughout. Filling the bag, a little at a time, with a smaller container, we began to fill the bags, occasionally lifting the bag vertical to allow gravity to compress the fill and pulling the bag up to avoid wrinkles. In ending each bag, fill to the desired length. When ready, sit on the end of the bag, pulling the end vertical. Twist the end, compact the side with your hand or a stone, and lay the bag down, tucking the twisted end underneath itself. Adding PVC pipe slightly wider than the bags for drainage, we compressed each bag until they were solid using a heavy tamping tool. We created a 3.5 meter hybrid wall section by running 3 layers of earth bag direct over the tire construction. We began the wall finish by filtering the clay earth to remove large material. Using this refined clay, we added 1 part clay, 2 parts sand, and 1/2 part concrete. Additionally, adding in 1/2 part water, the first finish coat is then ready to apply. This is done by employing a throwing technique. This coat must then dry for 24 hours before a final coat is applied. To apply this final coat, use the same throwing technique as before, followed by a hand patting until the surface is even throughout. Lastly, smooth by hand until a desired texture is achieved. In the final stage of construction, broken glass found on site was added, along with a planter, to enhance the aesthetic component of this project. Given our time constraints, we did not construct any portion of the wall with cob and bottle. Instead, we chose to finish the tires of the hybrid section with super adobe, adding a flower pot feature and creating a broken glass mural. The final wall is about 16 meters long, separated into 4 sections by existing trees. The steepest 2 sections were tire construction. The next was a hybrid section with both tires and earth bag, while the last section consisted solely of earth bag. This wall addressed design problems of slope stability while employing local, available, and sustainable materials and methods.